This meeting is being recorded.
In this next video from chapter 17, we're now going to take a look at another aspect of aqueous equilibria, something called the solubility products. So let's take a moment here, and as we're asked here, to consider the equilibrium of a saturated solution of barium sulfate in water. So what would that look like if we were to draw this out? So we have our barium sulfate solid. We're going to add that to water, and then we should expect our salt to ionize, and we'll get some barium ions, so Ba2 plus, aqueous, and then some sulfate ions as well. Also in aqueous phase, we know because we dissolved in water. So we're going to be shown here our equilibrium constant, because we have a solid dissolved in water here, will look like this. We won't include the solid in our equilibrium expression as our reactant. So our equilibrium expression will not have a denominator, and we call this the solubility product equilibrium constant, or KSP, and this would be the concentration of our product, Ba2 plus, times the concentration of our sulfate, SO42 minus. And again, we don't include any reactant in our denominator here because it's a solid. So only the aqueous will be considered for this example. And so again, this is my solubility product, and if I needed to look up values for KSP, there is this website provided here. This link has a table, and the KSP found for barium sulfate from this table is 1.1 times 10 to the negative 10, and these are always going to be at room temperature, so 25°C. So let's take a look at this example below, exercise 10, and any of the values that are not given, I would have pulled from that table, so from this website here. So if you want to navigate to that website as you follow along, let's get started. So we have barium carbonate, solid. We throw that in some water, and we get our barium 2 plus, aqueous, and then we have our carbonate 2 minus, aqueous. We look up our value for KSP, and we write our expression like so. So very similar to the barium sulfate example above, we're going to have our concentration of Ba2 plus times the concentration of carbonate. So hence where we get a product here. So whatever's soluble ends up over here, and then we take the product of that. So that's where the name for our KSP comes from. And then we're going to set this equal to what's given in the table. So now if we needed to solve for something, we could. We have our value, we have our KSP expression. Let's take a look at what silver sulfate will look like. So silver, if you recall from ionic compounds, is generally a +1 cation. Sulfate's -2. So our solid silver sulfate would look something like this. And we should note that these salts are only slightly or sparingly soluble. So they do not completely ionize like a salt that you might have considered to be a strong electrolyte. So what do we get over here? We get some silver ions, aqueous, and then we're going to get some sulfate ions, also again, aqueous, AQ. So what does this look like, our KSP? Again, we don't need to include our solid in our expression and our denominator, so our KSP equation would look like this. We'll set that equal to the value that I pull from the table, 1.5 times 10 to the negative 5. Notice these K values don't have any units like previous K values. We've seen they are unitless constants. So last but not least, we have our iron 3 phosphate. So that would mean that this is +3. Phosphate, I know, is -3. So this is our solid here, FePO4. When this ionizes, I'm going to get Fe3 plus and PO4 -3. Of course, we're in solution here. And so what does our KSP expression look like here? We're going to take the concentration of iron 3 plus and our phosphate 3 negative, and we're going to set this equal to one last value that we pulled from that table. So we're going to have times 1.0 times 10 to the negative 36.